Alright, so we start again. And so we have talked very vaguely about L1 and L2. What is their impact? They try to make your models simpler, right? So regularization means we use regularization to make our models simpler. And when you have two models for the same thing, right, you always prefer the simpler one that explains, so simpler one has to explain the data well, contain the distribution well. So regularization makes our models simpler. And when you have two models, so let me put the previous statement, when you have two models with the same accuracy, you prefer the simpler one. Now, how does dropout work? So let's say, and this is important because this is what we keep on doing throughout deep learning. Whichever model you will see, we will always have dropout as a regularization, as a regularizer, and not really L1 or L2 per se. But almost all regularizations, they tend to have the effect of L2. Almost all, not everyone. So dropout. How does dropout work? So let's say you have this is my neural network. Now, if you were doing L2 regularization, what will you do in this case? If you were doing L2 regularization, what would you do in this case? If you were doing L2 regularization, what will you do in this case? Squares, right. So you will, whatever this original J0 was, you will add lambda times Wi square, okay, and there are a lot of them. How many weights are here? 9, 18 and 9 again 27, right? So you will have 27 such terms, Wi's including Bi's, okay. Now, so one way is to use this particular factor, this one, this is the regularizing term, but you don't do that. What you instead do is, let's say, so what you do instead is, let me just draw this again. So what you do instead is x1, x2, x3. right. So what is happening? This is my neural network. How is this changed? And these two networks can be said to be derived from this upper one. What is this guy? How is this related to this guy? How is this neural network related to this neural network? So if in this neural network I drop this neuron and this neuron, I get this one. Is that right? Okay. In this neural network, if I drop, I wanted to drop. So wait. So let me. I drop from this side. No, but this is fine. So let me just do this one now. So this one, so from here you can go here. From here, how do I go here? Just this neuron is dropped. Okay. This is dropout. So you take a bigger neural network, you randomly drop some of the neurons, right? So in this case, we have not done or we have not used dropout in this layer. So maybe no dropout. And in this layer we have used dropout. In this particular example, in both the layers we are using dropout. Okay. So it is up to you to decide where do you want to do it, but in general you would do it everywhere. Okay. Now dropout. Can you do dropout here? Can you do dropout here? Why not? Why not? Yes, you are right. You are right. You don't want to do dropout here, but why?
We are training with it.
So you are right, because you have thought that you need these three features to do something, you can't do dropout here. If you could do dropout here, maybe what you would do is, so let's say there was some X4 feature as well. You decided not to keep that. So that you will already do beforehand, before even starting this neural network. So you don't do dropout in the input layer. Can I do dropout here? So you can't do dropout in input or output layer, and this, the function that we have been always saying, that this is the function that my neural network represents, because this is my function f that takes input to output. So you can't really drop anyone here or here. So no dropouts here, no dropouts here. Okay. Now help me understand, why should this have a regularizing effect? Have you done decision trees before? Right? So what are random forests? You don't answer this, I don't talk about this. Yes. What are random forests? And what are ensemble of these things? Right. So this has the same effect. Won't explain through those things, we'll talk about just this one. So tell me, what is the relationship between this and this and this and this, apart from the fact that you just dropped a couple of neurons? More relationships, I mean. Yes. Parameters are less. What does that mean? Which one is more complex, this neural network or this neural network? This one is more complex. So just by dropping out, you are making it simpler. And we say that when a complex network is turned into a simpler network, it is expected to have a regularizing effect. Okay? So, this has a sometimes I am writing S, sometimes Z, regularizing effect. Okay? Same thing here, has a regularizing effect, and this term regularizing effect you will see in a lot of papers, right, because there is no one thing that has this effect. There are so many things that has this effect, but in today's world, in today's neural networks, from whatever limited I know, the only thing that is used exclusively for regularization is dropout. Okay? Now, so how does this help me? And how will this even work? Because this guy had all these weights, you suddenly drop something. So, you have to help me figure out what should be the algorithm for doing this simple thing. This is a very simple trick and very powerful one. So, the moment a neuron goes to 0, all the weights corresponding to that go to 0. So how do you, have you done dropout before in ML? No. So then we talk about this in a little bit more detail. So tell me, what you do is the following. Help me figure out what is my gradient descent until convergence, compute J, compute grad J and update. Okay. Where would you fit dropout in this case? See, my training loop is fixed. It is until convergence, compute J, compute grad J and update. Ab you might be doing it in different manner. If you are using RMS prop, your updates will look like a different equation, but it will still fall into this broad category. If you are using batch gradient descent or stochastic gradient descent or mini batch gradient descent, you will have a couple of more for loops, but it will still fall into this broad category. So my question is, where should I add dropout in this case now? So while making a forward pass, while making a, and you do dropout, so okay, but nobody is asking anything. Which network is the one I will finally end up with? And I am giving you just these two examples. So let's say my dropout is this. In this one, the probability of dropping a neuron is 1/3. In this one, the probability of dropping a neuron is 1/3. On an average, what will happen? So when I make a forward pass here, what will happen at this layer? One of these neurons will go away like here. So this goes away. Let's say this one goes away. At this layer, this one goes away. And it so happens that in this case, there was nothing, right? So even this case also is possible, that you don't really drop out anything in this case. Tell me, how do I compute my J for this particular example when I have dropped out? Do you see the question? The question here is, earlier when I was doing until convergence, compute J. So you were computing J for this guy. You will do Wx plus B, W2 A1 plus B2 and so on. But now in this forward pass, you have dropped this guy. How do I handle this? So for one example, you are dropping it. For another example, you are dropping this guy. For some other example, you are dropping this guy. And similarly, so right now let's think of it this way. For every forward pass, for every example I give input to my neural network, I may drop some of the neurons. What am I essentially doing? Yes. For one, let's say I have only two examples in my training data set. Okay. For one network was this, for another one network was this. Which network am I eventually learning? This one or this one or this one? This one? Why so? So if I take union of these two guys, will I get this one? That means I am learning all the weights that are present in this particular network, right? So this is the one I am essentially learning. Next time, let's say, so first iteration when you came this side, this was the dropout for my first example, this was the dropout for my second example. When you came for the second epoch, let's say this happened for my second example and this happened for my first example. All these kind of things can happen. Okay. How does this thing help me regularize? कुछ पूछो बोलो नहीं अभी तो मैं इसमें ज़्यादा इंटरेस्टेड हूँ कि कुछ लोग कुछ पूछो दे हैव लॉस्ट मी यू नो मे बी 30-40 मिनट्स अगो दो मिनट रुक जाओ यस एनीबडी वांट्स मी टू रिपीट समथिंग चलो हाँ कंटिन्यू my focus is to be able to understand, because see if we have just too many things, whatever you said is right, but if we just focus on too many things, एक बार अपनी अभी अपना hypothesis क्या था, if I make a network simpler that helps in regularization. How is it making my network simpler? We have not decreased the number of parameters. That's the whole point. We have not decreased the number of parameters. My number of parameters are still the same as in this network. Right? So essentially if you see, you are updating lesser on parameters. Some parameters are not being updated that much. Right? So it turns out that if you train for too long, some parameters, not all, some of them might get trained too much. So for example, it might, so and all these are statements as I say. So for example, there was an over reliance on this particular neuron to do something, right? Whatever it was doing in the end, let's say there was some over reliance on this particular neuron, Once you drop this, what will this neural network do? It will try to make up for this guy, and whatever this guy was helping me in learning, it will have to do through remaining parameters only, right? Same for this guy. Let's say this guy had some special function and it was over relying on this. What will happen in this case? If I drop it out, then this neural network will have to take care of the things that was being done by this guy. What does this actually mean? None of your weights will grow beyond a certain point, because you never see, if weights grow beyond a certain point, what does it mean? That there is too much reliance on that, right? But the moment you start doing this, what will neural network do? So it wouldn't depend on just one neuron for too many things or for one thing either, right? Second thing that you see, what is an ensemble of models? What is an ensemble of models? So basically you train on different networks and take average of all of them, right? This is what you are doing. You are training on different networks and then finally you take average of them. Because of limited space and limited time and limited whatever, I draw only these two. How many sub networks can you have for this guy? With this, let's say we are dropping exactly one neuron here, exactly one neuron here. How many neural networks can you get from just this one? So as I said, it's not probability 1 by 3 anymore. I will with probability 1 drop one of the neurons here and one of the neurons here. How many neural networks can you get? Pakka? No. So in how many ways can I drop here? 3 ways, right? In how many ways here? 3. So what will be the resulting thing? See, if I drop here, right? So how many do you get? 9, okay? And let's say if I have n neurons here, how many different one will you get? And if that you will get only if I say I will be dropping exactly one neuron. If I say I can drop 2 neurons, will it be n square still? It will be much more than that now, right? So the number of sub networks that you have are exponentially many. So eventually when you will have lot of data, you start with this particular neural network, but eventually you will be training a very few number of neural networks because you can drop anyone. So you won't be training this at all. What you will be training is some sub neural network of this guy, and the bigger the neural network, as we said, you have exponentially many sub neural networks. So almost every batch will be trained on a different neural network, okay? And then you take, so this basically, this whole process is equivalent to taking average of all and then finally putting the weights here. So do we understand the forward pass a little bit now? What is forward pass? I can drop any of these guys. Now my next question is, how do I handle back propagation in this case now? Because in the back propagation we can't say, so in the back propagation I will have to somehow I mean, how do I handle back propagation? It's easy. How do I handle back propagation? You will backprop for this guy. You don't have other weights here. When you are using this network, you backprop for this guy. Now my last question, no, maybe not. What do I do at the test time? So at the test time, can I drop a neuron? No. Okay. You don't drop out at the test time. So maybe write this down. Okay. So okay, so I think with this I am more or less done with whatever I had to say about dropout. But I will make separate videos for L1, L2 and dropout that require more than. So, anybody who is interested in knowing more about this can go through this. Huh. You can do whatever. See, that's the beauty of deep learning, you can do whatever you want, but then you should be able to handle that thing in your code. Okay. So, you actually, one thing that I have not talked about too much is probability of dropout. So, when you write TensorFlow code or PyTorch code, you will always have a parameter here, right. So, for that for layer, how much is keep prob probability. So, this probability is how many do you want to drop or how many do you want to keep. So, if you keep the probability of dropping, let us say 0.5, what will this mean? If you have 100 neurons here, 50 of them will go away, right. If you, and you can keep different probabilities for different layers. So, here you can have keep prob equal to 0.5, here you can have keep prob equal to 0.2. So, in this case you will drop statistically half of them, in this case you will drop only 20% of them. Okay. Now, there are other ways of regularizing, but as I said, every paper you see, every good paper you see, it might introduce a new way of doing regularization. They might figure out that this thing has regularization effect as well. Now, in case of computer vision, see, if I increase my training data set, that also has a regularizing effect. How? If I increase my training data set, that has a regularizing effect. How? No, so let us say, so you have training examples equal to 100, you have training examples equal to 10,000. So, increasing training examples, maybe better. See, you have 100 points versus you have 1000, 10,000 points. Why will this have a regularizing effect? See, in the end, so if I give you just 2 points of a distribution or 3 points, right, most likely you will overfit. So, let us say if I give you 3 points, what will you do? So, if I give you, I have just 3 points in my data set, what will you most likely do? Guys, if I tell you that I have just 3 points in my data set, what will you most likely do? Maybe pass through all of them, because even this is a very simpler one. But now if I give you, more points, you probably won't go for this one, you would this one. So, adding more training, so that is why they say you should have as much training data as possible, because that will help you generalize well, right. Initially we had just these 3 points, we have no idea which distribution these 3 points are being drawn from. More points will help you have more confidence in which distribution you are talking about. Okay. Next, so in computer vision what you can do is something called data augmentation. So, how do you increase data in computer vision? You can do rotations, but you can't do too much of them, right? So you can do rotations, maybe 3 degree, 4 degree, 5 degree. What else? You can take mirror images, you can do a little bit of distortion and so on, whatever works well for your application. So, but in the end, what is data augmentation doing? You are just increasing the number of training data. So increasing the number of training data is one of the very good regularizers, because it basically changes your distribution. It gives you more confidence in which distribution all these points are drawn from. The lesser points you give me, the lesser I have confidence. More points you give me, I have more confidence in which distribution are these things drawn from, right? And that's the race for, you see LLMs, there they have, so their billions of tokens are nothing these days. You are training LLMs on 15 trillion tokens, 45 trillion tokens and so on, right? Okay, so we have augmentation. Early stopping. So how does early stopping help me? So this is my validation set, this is my test set. How does early stopping help me? Of course, this is my J end. Huh? So I am saying early stopping has regularization effect. So first of all, tell me where should I stop if I were to do early stopping? Right. So where I have, so maybe you guys tell me, somewhere here or even closer? Can even stop here? You of course don't want to stop there, because this is maybe a, so maybe this network, so just a second, let me draw it better, because most of the times you won't see it like this. So let's say you have something like, yes, so maybe somewhere here, okay. Basically early stopping means what? I don't want gap to be this much, at the same time I don't want to train for very little, okay. So you stop somewhere around, you know, where this bottom was there, because you couldn't get your training on validation set better than this one, right. So somewhere around you stop. This gap is just too much, okay. So maybe you need other ways of regularizing as well. Maybe a better example for early stopping would be, right. So in this case I should maybe stop here, okay. Okay, now there is yet another thing. यार ये 2 घंटे की क्लास सच में टू मच है, बट तुम लोग तो 1 घंटे में ही बोर हो रहे थे, 1 घंटा भी 1 घंटा नहीं था वो तो, हाँ किसको ब्रेक चाहिए, जाओ. Alright, so we talk about normalization now. So we do normalizing the training data set. and this is again, this is something you will see everywhere, right? Whichever PyTorch TensorFlow code you will see normalization. So particularly computer vision, okay, you have something like this. These are, so this is a so I have two features, x1 and x2. What does this curve tell me? So what does this plot tell me? So x1 has higher what? Right. Okay. So how can I talk? Actually, yeah, I was not able to draw this. Else, what you can have is, you can have that, you know, elliptical shape kind of thing, and all your data fits in just there. And we know we have problems with ellipses. What problems do we have ellipses? Whatever we had during optimization as well. So we have problem with lesser variance in one direction, and so higher variance in one direction and lesser in the other. So what you can actually do is, now, so maybe I will draw it here only. Sorry. So what you do is, what are you doing? Shifting x-axis. What else would I do? Will I just shift x-axis? So should I just shift x-axis? Maybe x, so not just x1 but as well x2. So this part is done. Does it have any impact on my training data set? No, it still remains the same. What I have done is, so let us say the centroid of this was somewhere here. All I am doing is I am shifting my coordinate axis to the centroid. Okay, this is all I have done. What next? I see lesser variance in this direction, more in this direction. How can you change that? Adding, right. So now think of it this way. See, adding more data points is something that you will do initially. So before trying all these things, if you can make your data set from 100 to 10,000, that will be your first job. Do that. Now that you are left with this, you probably don't have this option of increasing training data set. You have tried everything. Now what do I do? So this is on top of that. So what you do is, first we compute mean, as we have already done here. So compute mean mu equal to okay, this is what we are just doing. Now Okay. What will be the effect of this particular thing? See, right now you have just shifted the coordinates here. This thing was done by this guy. Okay. You just shifted the coordinate there. What else you do now? So, this thing basically spreads out. Instead of being something like this whole thing will become, more spread out. So, your points, the same points will get more spread out. And so on. Okay. Same data, but now you are representing it in a different form. So, now you have comparable variances on both the directions. So, the representation of data looks more circular than a elliptical one. Yes. A little bit in this direction as well. Okay. What else? So, I have 5 minutes and I can do one small thing in 5 minutes. Last thing. Have you heard of this thing? What are vanishing or exploding gradients? So, I have x1 to xn as input, I am doing binary classification, I have 100 hidden layers in between, right. Give me an equation for del j by del w111. How many terms will this partial derivative have? Do I need this partial derivative? Do I need this partial derivative? Do I need this partial derivative? Yes. Why? Because in order to update W111, I will need this particular partial derivative. The equation is W111 equal to so I need this partial derivative. This partial derivative is sitting here, somewhere here, right? Because this is my first hidden layer. So, I have my W1 matrix sitting here. How many terms will be here in this chain rule? You do not have to give me exact number, but just give me the order of numbers you will have here. How many? Remember, when we had 2 layers, you had roughly 5. So, for every layer you will have 2 partial terms. What are they? Del A by del Z and del Z by del A again, right. So, for every, so del AL by del ZL, del ZL by del AL. So, for every layer you have 2 partial derivative terms. You have 100 layers here, you will have somewhere around 200 terms in this partial derivative. Now, what happens if let's say all of these partial derivatives are lesser than 1. Let's say you are in a very bad case. What will happen if all these 200 terms or a lot of these 200 terms are lesser than 1? 0.1 into 0.1 is 0.01. 0.01 into 0.01 is 10 to the power minus 4 and so on. Okay. So, if you have too many terms that are lesser than 1 and if you multiply them, you might have a numerical underflow. So, forget numerical underflow, this guy will go to 0, yes or no? And what's problem with this? You want this guy to go to 0, but not for this reason. But this guy has gone to 0, will you be able to update W11? You won't be able to update W11, this is called vanishing gradient problem. At the same time, if all these 200 terms are greater than 1, what will happen? Those values will be very high, right? So, your update will be super big in this particular direction. You don't want that either. There is an easy way to solve this problem called gradient clipping. And I won't talk about this problem later because this is not a problem. Gradient clipping. So, algorithm is this. If grads are greater than or equal to 100, grad equal to 100. Just these two lines will do it for you. So, if my gradients are larger than a quantity, I just clip it to that value. But can I do anything here? No. Vanishing gradient remains a very big problem today. Not today, but we'll talk about it, how to deal with it. Okay. I think that is it for today.